right, welcome everyone. Glad to see all these faces here. So just to let you know, Forrest Brazeal is somewhat local. How far away are you? 3 hours?
About 2.5 hours.
2.5 hours, so yeah, somewhat local, and he is a serverless hero, so he's here to talk about NoSQL data design, and I think that's a really cool topic. I've learned a lot about it myself over the last couple of months, and every time I do another project, I learn a little bit more, so it's pretty cool getting into that. And I think it's a good topic for everybody, no matter who your cloud serverless provider is. So without further ado, I will pass it off to, well, actually one more thing. I just want to say sorry about the janky stream for everybody watching the stream. I tried to capture cards and stuff like that working. It'll be another month before I get everything that I need, I believe, to work here. So for right now, we just have the stream of the video, but if you want to look at this later, you can go on YouTube, and it's just Triangle Serverless under there. I will put this on the meetup though, so everybody has it. And that's it. All right. Take it away, Forrest.
Thank you very much, Patrick.
And thank you, of course, to IBM for the space. This is fantastic. All right, well, it's good to be here in the, what do you guys call it, the Triangle? Durham, what do the locals say? Yeah? RTP. RTP? Okay, it's great to be here. All right, I want to get started tonight by telling you a story about the most embarrassing moment of my IT career. I don't think I've ever told this story in public before, so we'll see how this goes. So return with me to the glorious days of yesteryear. I was 18 years old. I was working a summer job on the help desk for a medium-sized managed services IT company. And part of my job occasionally was to leave the help desk and to take a server or a patch cable or something and to deliver it to one of our field engineers who was out working on a client site. I liked this part of the job a lot because it was less boring than sitting on the help desk. So one day, one of the engineers comes in, throws me his keys. He says, hey, go out, take the company car, and deliver this piece of equipment. I said, okay. So I got in his car, and I got it on the freeway. And I had been going a little while, and I noticed that the car was having trouble maintaining speed. It was kind of juddering a little bit from side to side. But I didn't think too much of it until I went to get off the freeway, and the exit ramp was a steep downward incline. And I put my foot on the brake, and nothing happened. If you've ever had the misfortune of being in a car with brake failure, you know that it plays tricks on your head because you expect that when you put your foot on the brake, the car is going to slow down. And when it doesn't, your brain tells you that you're speeding up. So I shot down that incline at about 50-55 miles an hour with every hair on my body standing up on end. Took a hard left turn at the light at the bottom. Thankfully it was green. Felt both of my right wheels come up off the pavement there as that happened. I went down about another 150, 200 yards, went through a second light, that one was red, and eventually ended up running out of momentum in the parking lot directly opposite the building that I was trying to get to all along. So that was cool. What I should have done there is just like walked away in slow motion, but instead I called my boss and he came out, took a look at the car, called the dealer came and took the car into the dealership. They called us and they said, what did you do to this vehicle? They said when we brought it in, the brakes were so hot, they were literally glowing blue. Of course, being 18 years old, I said, I don't know, cars. And I went on with my IT help desk life. And then the fall came and I went back to school. And then about 6 months later, I sat up in bed in the middle of the night and went, oh, I took that poor guy's car on the freeway and drove it like 15 miles with the emergency brake all the way on. And then I graduated from school and I became a SQL Server database administrator. My name is Forrest Brazeal. I do not have that job anymore. I have a different job. I work for a company called Trek 10. We're an AWS Advanced Consulting Partner that focuses specifically on serverless solutions. We're one of the foremost shops at designing and building serverless stuff on AWS. You may know my name if you are involved with A Cloud Guru at all. Anybody done A Cloud Guru training courses at all? Yeah. So I write for their community publication. I do a cartoon series for them that you may have seen floating around. And I'm also, as Patrick mentioned, what's called an AWS Serverless Hero. There are 10 of us in the world right now. And that just means we go around and educate, advocate for these technologies, try to keep people from treating their serverless apps the way I treated that poor Toyota Matrix back in the day. And so it is in that spirit that I would like to present to you tonight a talk called, what just happened there? NoSQL Design Patterns for Serverless, otherwise entitled How Not to Drive Your App with the Emergency Brake On. because, oh yes, there will be cartoons in this talk, I forgot to tell you. So if there were ever two technologies that lend themselves to being abused by people who are not sure what they're doing, it would be NoSQL on the one hand and serverless on the other, and I can attest to that because frequently I have no idea what I'm doing when I'm working with them. So I'm going to talk to you tonight in two parts. The first part will be a little bit more general, theoretical, high-level, serverless and NoSQL, an eventful relationship. See what I did there? And then part two, we're going to dive in very specifically onto a particular NoSQL data source as it relates to serverless, that being Amazon's DynamoDB. And I've broken the talk up this way not because either of these parts would not be enough to fill this time by themselves. They absolutely would. In fact, we're going to go pretty quickly through some of this stuff. I've done this because I'm very sensitive to the fact that we have people here from a wide range of technical backgrounds. You do different things at your day job. Not everybody, for example, is building on AWS. I'm well aware of that. So hopefully, especially part one, everybody will get a lot out of this. I'm going to try to keep it as cloud agnostic as I can. And then part two, even if you're not using DynamoDB, hopefully you'll be able to take away some design principles there as well. All right, sound good? Oh, and then one more thing, questions. I'm going to try to pause repeatedly for questions. So try to save a question if you have it until like 2 minutes later when I stop. But if it's just burning and you can't wait, raise your hand. Sound good? All right. So I'm going to not bury the lead. I'm going to start with the most important question of all here, which is 5 years or more after what I would consider to be the peak of the NoSQL hype bubble. Why should I use NoSQL when relational databases are still right over there, where they always were, working just about as well or not well as they always did? What's the point of getting into all this newfangled stuff? And I will tell you right now, the answer is a resounding, it depends. Thank you very much. That concludes the first part of my talk. No, it does not. Yes? No. So I want to make it clear, though, that a lot of the things we're going to talk about tonight are not prescriptive. They're very dependent on your use case, so keep that in mind. But let's start by diving into the SQL versus NoSQL question a little bit and just make sure we're on the same page. Because when we talk about SQL, the structured query language, that's a declarative language that we're talking about. A lot of times people use it to refer to the underlying relational database mechanism. But in reality, you don't necessarily know when you say select star from X table where such and such a condition is true. You don't know how the database is implementing that query under the hood when it goes to execute it. There's a query optimizer in most traditional database management systems, and it's going to run that query on your behalf. You don't have to specify the index when you make the query. The database engine will make that decision for you, and that works great, except when it doesn't. If you've ever been a SQL Server database administrator, such as I was at one point in my career, you've probably had to deal with like execution plans and slow queries and all that frustrating stuff where you have to dive in and apply some intelligence to the situation. Now, NoSQL, on the other hand, the way you query the database tends to be much more tightly tied to the underlying architecture and the organization of the data. To use DynamoDB for an example, because we're going to talk about that more later, when I make a DynamoDB query, I've got to tell DynamoDB what index or table partition that I want to use. I've got to specifically structure my data inside the table so that it will be optimized for the query to work correctly. And that, again, works great as long as you know what you're doing, which a lot of folks using DynamoDB, including myself when I started out, absolutely do not. And I want to correct one other misperception here up front and say, a lot of times I think that we tend to place SQL at one end of a spectrum, relational databases at one end of a spectrum, and NoSQL databases at the other end of a spectrum, and never the twain shall meet. And there is a spectrum, but that's not quite how it looks. It looks more like this. At one end of this relationship continuum, you have databases that have fewer relationships, and that would be what we would call, as a class, document databases. MongoDB would fall into this category. DynamoDB, which is a key value store, would be here. Some of the models of Cosmos DB, or even, dare I say it, the new Amazon Document DB. Believe it or not, that's a document database. These are all databases that are really good at denormalizing a bunch of information about an entity and putting it in this giant bucket where you can grab it. They're not so good at reflecting relationships between entities. And then all the way at the other end of that spectrum, what do we have? Not relational databases, but a different type of NoSQL database. Graph databases. These are hyper-optimized for relationships. These, n-dimensional friends of friends of friends, 6 degrees of Kevin Bacon kind of stuff. And relational databases fall somewhere in the middle. They're pretty good at reflecting relationships. They're pretty good at dealing with lists of entities. And that's one of the reasons that they've been so successful and maintained so much developer mindshare for so many years. They will compromise and get you just about anywhere you need to be for a lot of use cases. Okay. So that's a really, really lightning overview of the NoSQL concepts that we will need to go any farther. Any questions about that? All right, so now let's talk about what we're all nominally here to talk about. Since this is a serverless meetup, let's talk about serverless. And I want to dive into some characteristics of a serverless system so we can understand how this relates to our database choices. What does a serverless system look like? It tends to have, and I'm talking about FaaS here, functions as a service primarily, so think things like Lambda, Azure Functions. These systems tend to have arbitrary request rates. That means that I should be able to go from nobody calling my Lambda function to scaling up to perhaps thousands of concurrent invocations, back down to 0 very quickly. That should be totally normal. That's a common pattern for serverless compute. These systems should be fast evolving. They should have lots of small parts, i.e. microservices. It is the case that because of the cost model of serverless, you will often be able to spin up, multiple different prototypes of a system. You'll be able to A, B, C, D, E, F, G test it very cost effectively in the cloud. So you'll often want to kind of design your system as you go along. It's also the case that serverless systems don't have a lot of best practices yet. So a lot of times they're fast evolving because a new service gets released or an update gets released to a service after you just built the thing that now you don't have to build anymore. And then lots of small parts, microservices should make sense because these are functions. They're about as small as you can get. I don't know why I keep doing that, sorry. Okay, there's a picture mute button on this, that's what I'm doing. So these systems tend to be stateless, and I say stateless-ish, because even though serverless functions run for a short amount of time, they tend to be kept warm, at least Lambda functions do, between invocations to some extent. So if you have some state that you can put in global space, cache it between invocations, you can have some performance wins that way. But you're not going to do anything really long-running in a function. You're not going to hold open a connection to a database that's stateful. And then finally, serverless compute systems tend to be event-driven. There's no polling. It would be a huge anti-pattern to sit there in a serverless function and poll a database system. You don't want to do any work or pay for any work until you actually get called. Those are all characteristics of a serverless compute system, and every one of those characteristics affects the way we deal with data. I'll show you what I mean. Arbitrary request rates implies we really want a database that can scale really wide, really fast. Serverless compute systems can trivially scale to a point where they can knock down any downstream system that is not ready to access them. Has anybody ever had a problem like this, where you've scaled out wide with a serverless function and you've blown away some queuing system or some database or something like that? Very, very easy to do, scary easy to do. You need a database that can handle that. NoSQL databases tend to shard horizontally really well, particularly those that are built on the Amazon Dynamo model, such as Cassandra. Fast evolving corresponds to a database concept called schema on read. Anybody know what schema on read means? Have you heard that term? A lot of NoSQL databases, we say they're schema-less. And that's not really quite accurate, because let's be honest, all data has a schema. Your application pulls it out of the database, it expects it to be in a certain format, right? So we really have two options: schema on write, like a traditional relational database, where we place our data in and it's validated at the time we write it by some enforced schema, referential integrity and all of that. And then schema on read, where we throw the data into the database, we don't care how it looks, but when we pull it out, when we read it, the application had better be able to process it in a form that it's familiar with. So these fast evolving systems, if we can defer that data access to read, we may have some advantages. There is actually a microservice concept in data. Polyglot persistence is the super pretentious term that is used for that. Don't worry about what that means. We'll cover that more in a minute. I mentioned connection pooling already, but it's the case that for stateless functions, you don't want to have to hold open a long-lived connection. If you had some sort of connection pooling proxy, that would be one thing, but you don't want to maintain that in the function itself. So an HTTP API would be an ideal way to access a database from a serverless perspective. And then just as serverless functions are event-driven, you really only want to pay for compute when you're using your database system. You'd like to be able to scale to 0, just like you can with your functions. So given all of that background, I would like to present to you a manifestly ridiculous analogy, which is to say that FaaS, functions as a service, is to compute what NoSQL is to data. Now that analogy breaks down if you think about it for more than like 3 seconds, but don't think about it, just hear me out. On the left side there, where you have a server or a relational database, both of those things tend to be general purpose. Remember that center of the relationship continuum? These systems do a lot of things pretty well. They'll handle a lot of undifferentiated workloads. They scale vertically because they're giant blobs of compute, usually, giant blobs of capacity. You want to pack a lot of stuff in there. Have you ever had like a big Postgres database that had a bunch of tables in it that didn't relate to each other at all? Like you're not even using the relational components of the system. You just threw a 70 gigabyte table of access logs in there and a bunch of user data in there. Just because you have this big database and you provision it, you might as well use it. You know what I'm talking about? Yeah, so it scales vertically really well. And of course, the underlying architecture is designed for that because of the way it's optimized for storage. And monolithic architecture patterns happen as a result of that. But functions and NoSQL databases, they tend to be single purpose. They do one thing really, really well. A NoSQL database, if it's a graph database, it's not going to be great at doing document DB stuff. They scale horizontally. We already discussed how they shard out wide. And then microservice architecture patterns come into play here for both the functions and the NoSQL databases. And that brings us back to the concept of polyglot persistence. This is a fancy and annoying way of just saying that you may want different access patterns for different services that you build. Cosmos DB gets this really well with their concept of the multi-model database. But it should be easy as you're evolving your serverless system quickly, you're realizing new requirements, new access patterns. It should be easy to add different data stores to your app depending on client requirements. That's a challenge and a difference from the way we've traditionally thought, where you have the data layer of your app and it's some database underneath there, and everything that you have to store somehow gets shoehorned into that database. That's not a valid pattern in the serverless world past a certain point. And the big architecture pattern that I want to present to you in the first part of this talk to get around that is something called event sourcing. So let me stop right there. Questions on what we said so far? I know this has been a lot of theory. It feels a little lecture-y. There's going to be one more theoretical thing we're going to talk about, but there's going to be pictures, so it'll be okay. And then we're going to get into use cases, and I hope that will be more interesting. All right, so event sourcing. If you've not heard of it, this is the concept that everything that happens in the world can be represented as an event. Somebody walks through a door, somebody scans something out at a checkout line, that's an event, and it can be streamed into a system as some sort of piece of data. And all that data gets captured in something called a ledger. Ledgers are exactly what they sound like. Think about a financial ledger. If you make a transaction, you record it in the ledger, and it's immutable so that if somebody makes a mistake in the ledger or somebody maliciously changes something, you don't go back and erase that record, you add a new record, it's append only. And that actually enables you over time then to correct the record so that if you went back and replayed everything from the beginning, you'd end up with the exact amount of money that you have today. Now in the serverless world, in the data world, our currency is not dollars and cents, at least not directly. Our currency is events. And we place those on our ledger, which you can now begin to think of as a stream, perhaps something like Kafka or Amazon's Kinesis. So you place those events on the ledger, and that becomes the single source of truth, immutable, append only, for your entire system. And I want to correct a misperception here right off the bat that a lot of people get into when they start thinking about designing for event sourcing. And that is that this ledger, even though it's your single source of truth, it's not your quote-unquote database. Your applications aren't querying the ledger directly. You don't really query a Kafka stream or a Kinesis stream. Instead, you capture those events as they come off the stream in consumers. These could be Lambda functions connected to a Kinesis stream. These could be other types of worker functions. And then those consumers can take those events and place them into different types of data stores. Remember polyglot persistence? Could be a graph DB, could be a key value store. It might not be all of your events. It might not be a complete view of your events, but it's going to place it in such a way that the client that needs to retrieve that data can access it in the way that makes the most sense. We refer to these sometimes as materialized views. If you've worked with traditional relational databases, that may sound familiar because just like a view in a relational database, it's not the canonical source of your data. You've taken some view of that data essentially, and if the underlying data ever changes, you've got to refresh that view to get the latest again. And that's what we would have to do here. If there was a mistake in our ledger, or if one of these client systems went offline and we had to repopulate it, we'd have to run all the events from that ledger again to bring the end view up to date. Thus ends the theory. I know that seems really abstract and theoretical. How would you ever use this? I'm going to tell you about a real use case that I've actually been working on. It's anonymized to protect the client, obviously, but this is something that's really happening. And this is the idea of an inventory management system. Imagine with me that you have a lot of warehouses in lots of different physical locations, and you store lots of widgets in those warehouses. These are widgets of different shapes and sizes, different types. Other than a widget ID, they don't have very much in common. And you have lots of data sources throughout your enterprise that are recording different pieces of information about these widgets. Maybe something that scans them when they come into the warehouse. Maybe some of the widgets have little IoT sensors on them that are transmitting information about their location as they're taken from one warehouse to another, or they're being sold to an end user, or they're being onboarded into the system. And all of those little pieces of data are tied to a widget ID, and you have to mash them together to get a complete picture of the widgets that you have in your inventory. So you need a system that can do this. And what you really need is a couple of major views. You need a real-time view. Where are all of my widgets right now? What's the current state of my inventory, and how does it change over time? If I'm watching a particular widget in an end client and a change happens to it, I want to see that in my client right away. And then we have a historical view. What is the complete story of any combination of widgets that I've ever made? So you can think of this like the classic data warehouse use case. I want to do queries like, for a particular widget or widget type, how long does it typically spend sitting in a warehouse? Or how long does it spend traveling from place to place in this country given this set of parameters? Just ways to go spelunking with the business information you have to do historical, trending, predictive analysis. So that's what we want to do, and the architecture that I built to solve this in AWS looks something like this. I know that's too small for you to read. We're going to zoom in on the different pieces of it. But this is an implementation of that event sourcing pattern, and there's multiple NoSQL databases that are involved here. So we'll talk about how those are used. The event handling piece of this is based around a ledger, and in this case, the ledger concept that we're using is the CloudWatch event bus. Who in here is AWS focused, by the way? AWS is the primary cloud you use at work. Or you've used AWS a little bit in the past. Some of you have. Okay, it's actually fewer than it often is, but that's actually cool. So CloudWatch events, don't worry too much about this other than to say they actually are not ordered. It's not like a Kafka or a Kinesis stream. So this is in some ways not a true ledger. The events happen on this bus in any order. They're timestamped, so we can put them back together in the right order later if we need to, but it doesn't really matter what order they show up in on the bus. And there were a number of other architecture reasons that we made the choice to use CloudWatch event bus here rather than something like a traditional streaming service, but if you're curious about those, ask me afterwards. I can go into way more detail. So we place those events on the bus. We have a Lambda function there that's processing them, so it pulls the events off the bus, it validates them, and then it places them back on the bus with a tag saying that they're ready to be processed by any consumer of the bus. And that brings us to a big design pattern here, which is it's tough to keep the canonical record clean. Just like a financial ledger, we don't want to put things that are just obviously wrong in there. That helps, if we have to replay this or do auditing on it later. We don't want to break our ledger. So it helps to have a multi-stage pipeline for event processing. When I've implemented this with a Kafka-like streaming system in the past, I've had two separate streams, one for raw events, one for validated events, and then you have a Lambda function in the middle that just makes sure they're valid JSON and they're not disgusting. If there is a problem, those events go to a dead letter queue, SQS or something like that. And then it's the client's responsibility, the person who initially put that event on the bus, submitted it, it's their responsibility to fix the event, put it back if they so desire. So that's a good way to keep your canonical record clean. And there could be more stages in that pipeline depending on what you want to do. The real-time update flow. So we had two views off of this system. The real-time update flow is giving me the current view, where are all of my widgets right now. And that's just a Lambda function that reads off of our bus. And it's going to place our data into Elasticsearch. We chose to use AWS's hosted Elasticsearch service for this portion of the project. Who's used Elasticsearch before? Several of you have, yeah. Elasticsearch has the advantage of making it really easy to do full text searches on documents, particularly ones that have arbitrary attributes, which was the case for ours. We could index on a widget ID, made it really easy to work with, and then because we're just looking at the latest version of every widget, this isn't going to be an exponentially growing data set. So one thing you have to worry about with Elasticsearch is, you've got to provision that underlying capacity. It's not going to scale horizontally in the way that DynamoDB or a true NoSQL database is, but that's not going to be a problem due to the nature of the data we're putting inside of here. And yes, I'm aware that we'd like a serverless database to be truly capacity scaled, pay only for usage. Unfortunately, we do have to pay for provision capacity here, but at least we don't have to manage everything ourselves. So the other piece of this is the real-time update piece, the subscriber piece, and we did this using WebSockets, using an AWS service called AppSync. AppSync is a managed GraphQL backend. It also supports WebSockets. So whenever we made an update to Elasticsearch, we would go ahead and send an update to the AppSync API using something called a local mutation, and then any client that was listening on that widget ID would get an update directly to their browser or whatever the front-end app was implemented as. And a challenge here, which I've touched on just a little bit, is the question of eventual consistency. Anytime you're building an event-sourced system, you have to think so carefully about making sure that all those distributed views of your data stay in sync. There's a lot of ways you can do this. To make sure you converge on the correct answer, you can use timestamps, you can do conditional writes depending on what your data store supports, atomic writes, transactions. In Elasticsearch's case, they have optimistic concurrency control. They use versions of documents to do that, and we definitely relied on that. We also ended up having to timestamp every attribute of every document that went into Elasticsearch, so that if those records came in out of order, for example, update A came into a widget, and then update B came into a widget, but update B was processed in Elasticsearch before update A, we had to make sure we timestamp those attributes so we'd be able to sort that out in our consumer. Question?
Doesn't Cassandra handle the consistency issue?
Cassandra has its own methods for handling consistency for sure. Yep. So you just need to know how your particular data store handles consistency and just be thinking about it. Don't expect all these views to magically stay in sync because they will not. It's a juggling act. And I'm not providing a lot of prescriptive solutions. I'm just calling out that this is a problem. But the last view we had here was reporting flow. This is the data warehouse use case. Want to see a historical view of my system. So we flowed every event that came through the bus to Kinesis Firehose, which is a streaming service that sends all of our data to S3. And S3 you could really think of as the canonical view of this system. All of our events were stored there as JSON documents. So if we ever had to do auditing, we could go back and put those together piece by piece from S3. But that's not really something that you would query as is. So all that data went through a service called Snowpipe to SnowflakeDB. Anybody use SnowflakeDB or heard of Snowflake at all? It's a data warehouse product. The closest analogs to it would probably be Google BigQuery, AWS Athena. But it allows you to do SQL queries on unstructured JSON data in a wide column format. It's a really nicely priced, scaled capacity data warehouse solution. Worked really well for us. And the challenge that we ran into here, this really plays into that real-time update flow more than the report flow, but it's the idea of one client and multiple data stores. So it's the case that if you're using polyglot persistence and you're putting different types of data access, for example, historical data access versus real-time access, or perhaps graph access or something else, you're putting all those in different data stores, but you might have one client, one end user that needs to consume queries from several of those data sources. So it really helps to have a standardized API that abstracts that so the client doesn't even need to know what data source they're talking to. This is actually the use case that GraphQL was designed to solve. It makes it really easy to place resolvers behind your schema that are wired up on the back end, and from the user's perspective, all they see is the contract they have with that GraphQL schema. And I think that's interesting because it moves us back toward a narrow waist of data access. Anybody know the term narrow waist from the networking world? This is usually used to refer to IP, Internet Protocol. Think about all the things that speak IP, TCP, voice over IP, PC over IP. What do they all have in common? IP, right? Every network device speaks IP. And that used to be the case with SQL. Every database spoke SQL. The great NoSQL, debacle happened, not to put too fine a point on it, and everybody went different ways with their own APIs. We're moving back in the NoSQL community to having SQL as more of a standard for more of these data sources now, but GraphQL actually does this too. It's a SQL-like JSON expression, if I could put it that way. It's SQL concepts expressed as JSON that masks multiple data stores, which I think is an interesting trend to keep an eye on and can be a powerful pattern for you. Now, the beautiful dream, of course, would not be that. It would be a true serverless database. And here are the things that I would want in a true serverless database. I would want to pay only for the capacity that I use. I would want negligible cold start, meaning that when I do want capacity, I want it now. I would want it to stretch as wide as my compute will, so horizontally shard. I would want it to have an HTTP API. I don't want to maintain any stateful connections. I would want it to support all of my access patterns. No matter what I want to do, I would want there to be a nice SQL API or something that would let me do that. And then, of course, I'd want it all to be fully managed. I don't want to patch anything. I don't want to pay for anything or worry about anything below the layer of my data itself. Well, I shouldn't say I don't want to pay for that. I do want to pay for that. I don't want to pay people to do it for me, that work for me. That is a beautiful dream. I am not aware today that there is any database that comes close to doing all of these things. Although a lot of people are trying, and people have gotten close on some of these things before. There are databases that do 3 or 4 of these things really, really well. We're going to look at one of them next, and that, of course, is DynamoDB. So let me stop right there. That was the theory section, and I went through that at lightning speed, more so than I intended to. Questions? Yes, Patrick?
Do you mind going back to the real-time
Yes, indeed.
slide? So I'm curious, when did you when was this architecture set up?
So this is actually, we're still extending it, but probably September of last year.
All right. So like, and I know it's a 10,000-foot view, but like, would you take out the app sync part, since that's doing the WebSockets now, and change that to like a pure Lambda, since they support WebSockets? Like, I don't really know 100% what that one little block in there is doing, so it could just be...
Yeah, that's a great question. A GraphQL API makes a lot of sense for this type of a system for the reason that I tried to explain here. Excuse me. Which is that, sorry, not there, but here, which is that you have a single client that potentially needs to access multiple different data stores on the back end. And this system is built, by the way, I should have mentioned this, to be really easy to plug other data sources in. So if I later on wanted to have a DynamoDB consumer off of that event stream, it would be really, really easy to plug that in. Wouldn't have to touch any other part of my architecture. It just exposes my data as a different type of view. It would also be easy for me to extend my AppSync API and my GraphQL schema to surface certain queries that go back to DynamoDB. So I'm getting a lot more with AppSync than just WebSockets. Okay. But the fact that it integrates those subscriptions is really nice. Great question. Yes, sir.
So do you agree that GraphQL and Kafka and event sourcing are kind of a superset of the NoSQL database, and that they're really protocols that are stacked on top of that? And especially event sourcing, when you apply it to Kafka, you've got, you know, you talked about the issue of consistency, but you know, your connections can be looking at that data and sampling them at any period of time, and they can be any update. And they don't have to go and refresh or take another look because they're in a string, right? They're connected and they're going to get the data at some time. So they're looking at a table or a join at some point, and they're going to have to process that data in that instant, in that context.
I'm not sure I understood all of that, but I think you've got some good thoughts there.
I mean, GraphQL is a protocol put on top of some backend, and it may not even be a database, right? But I mean, it's to supplant a traditional RESTful interface to the backend in a more query-like or SQL-like access to the data, so that the front-end developer has more flexibility.
I think there's some truth to that. Yeah, this is definitely not a GraphQL talk. We could get into much more detail about that.
But it's also not a database thing, is I guess my point, is that you know, these aren't the back-end database concepts. In the future, I'm going to ask another question about my particular application and a database question. But you know, I think it's interesting, where does the work get done? And the work isn't being done in the database server. The work is being done in the client or the protocol layer, right?
I think there's an important truth there, which is, you know, a lot of people have said Lambda functions are just store procedures for the cloud. And I go in and work with clients that have a ton of business logic in the database, these massive store procedures. And it's a real challenge to migrate that out and move that into you know, a more decoupled structure. But you've got to take into consideration the fact that monoliths they have their place. They're easier to maintain in some ways. I wouldn't necessarily just recommend that people pull everything out of the database just for the sake of it, although it does provide you with some advantages. Okay, any other questions?
What is DLQ?
Oh, a dead letter queue. So some sort of queue where you can place events that you don't like and you want someone else to have to deal with that are not you. Yep, good question. We good? We have lots and lots of time here, so don't feel bad about asking questions. Okay, let's move on then to the next part of the talk, which is around DynamoDB, NoSQL relational modeling with special guest DynamoDB. And I sort of led into this a minute ago by saying there are a lot of databases that do 3 or 4 of those beautiful serverless stream things pretty well. DynamoDB I sometimes call the granddaddy of serverless databases, and I call it that not because of some magical properties that it has, but because AWS Lambda is the granddaddy of serverless compute. And so when the first serverless architecture started coming out, they were what? Lambda, AWS API Gateway in front of it, and then DynamoDB behind it. So it got shoehorned into a lot of serverless architectures, and there were actually some reasons behind that. There were some things that DynamoDB did and does well that make it a natural fit for serverless. It's fully managed, obviously. You're not paying a DBA to do the the infrastructure maintenance for you. It's key value store. It is an HTTP API based interface, so there's no SQL, there's no long-lived connections. You make an API request that encapsulates your data. That's really, really nice for serverless. Probably the biggest reason a lot of people have continued to use it. And then, of course, it does scale horizontally to billions and billions of items. For a long time, I was uncomfortable calling DynamoDB a serverless database because it did not scale on demand, and it did not allow you to pay for on-demand scaling. You had to set a provision capacity, whatever number of read or write capacity units that was, and you paid for that all the time, even if the database was sitting there and you were doing nothing. That is not the serverless way, and you should be ashamed of yourself if you call yourself a serverless database and you don't support on-demand scaling. Thankfully, DynamoDB has finally woken up and supported this. They had an auto-scaling concept for a while, but you still had to pay for provision capacity. Now, as of Reinvent 2018, they have on-demand. You pay nothing until you pump data into that database or read from it, and then your write and read capacity will scale up and down, no throttling. It's very cool to those of us who wish for this for a long time. It's also quite expensive, so use it at your peril. I am a recovering DynamoDB grump, a pretty famous one, as DynamoDB grumps go, if I do say so myself. I wrote an article about a year ago for A Cloud Guru called Why Amazon DynamoDB Isn't for Everyone, and it annoyed the DynamoDB team so much that they went out over the next 12 months and they implemented every single feature that I said was missing in this article. And every time they implemented a feature, I'm not even kidding, they went and messaged me to say, when are you going to update that article? Yes.
So quick question there.
Yes.
How do we compare it with other key value store like etcd or Zookeeper?
Sure. I think probably cloud scale will be the biggest thing. It's managed by Amazon, and it's able to scale out to billions and billions of records without you really having to do anything other than ask for it. Would be a big thing there.
Question you are about to touch it. Is it only for AWS if you're using it, or?
DynamoDB, the managed service, is only on AWS. It is based on a paper called the Amazon Dynamo paper. Dynamo is the name of an architecture that Amazon came up with. That paper has been implemented by a number of people, most notably Cassandra, but there are other databases that use the Amazon Dynamo principle as well. Mm-hmm. Yes. So the Amazon DynamoDB team went out and they implemented a bunch of features that I asked for here, such as they had problems around hotkeys, so they added adaptive capacity. They had problems around backup and restore. Their operationalization story wasn't that good. They went out and added a bunch of stuff around there. I'm not saying I was the catalyst for this. All I know is that they keep giving me grief about the fact that I wrote this article, so I think it must have touched a nerve. But they have not addressed what I considered then and still consider to be the biggest issue with DynamoDB, which is that it is darn hard to wrap your head around if you don't know what you're doing. Not even really their fault, it's just the way it is. There are some major gotchas for developers if you're starting to build on DynamoDB coming from a relational system. And the biggest one is that scans, which are effectively select star on your DynamoDB table, bad, bad, bad. Don't do it. It's easy. It's wrong. It will eat up all your capacity units. It'll be tremendously expensive. It'll be slow. It's not the way to use DynamoDB. Instead, you're supposed to use queries. This is where you take an index on the table. DynamoDB is key value, so it has a key, and then it also can have optionally a range key, a sort key that lets you pick a range out of that partition. Queries are the path to enlightenment. Doing those conditional lookups based on the range key, that's going to be fast and performant, but that's not intuitive to design your queries that way. Remember what I said all the way at the beginning about how in NoSQL you don't get to have the database engine make decisions for you. You have to specifically ask for what you want, and you have to be smart enough to design your database the right way. Not easy to do in DynamoDB unless you're really, really sure what you're doing. And then also, this really throws people for a loop. The DynamoDB best practices emphatically say you're supposed to have a single table per service. So where you might have an entire relational database with many related tables, you're supposed to put all of that into a single DynamoDB table. And the reason for that is, if you have multiple DynamoDB tables, remember, I'm accessing all of these over HTTP endpoints. I've got to make multiple queries from my front end. I've got to bring that data down. There's no concept of join in DynamoDB. It's a key value store. I've got to join all that data client side. I've got to have logic on my front end, spaghetti code that I maintain. So they recommend putting everything in one database. Then at least you get the data locality advantages of NoSQL, and theoretically you can construct that data in such a way that you can access it quickly. Theoretically, I say, but it's pretty hard to do in practice if you are new. So how limited is DynamoDB really? Given what I just said, is this really a valid use for a lot of serverless applications? Well, it's the best in the world at doing key value lookups at arbitrary scale. That's my point that I said just a minute ago. There's plenty of other things that do key value lookups. Nobody's doing it at the scale that DynamoDB is. In fact, when the Dynamo paper first came out, this was back in like 2007, I think, if I have that right. The reason Amazon developed Dynamo internally was because they had found that something like 70% of the lookups they were doing to their huge Oracle databases at Amazon.com were simple key value lookups. They were getting a record ID, they were getting the record attributes. And that's true for a lot of application access patterns, but not all. So given that we would like our serverless app to take advantage of the things that DynamoDB does well, such as, again, HTTP interface, scales really big, has on-demand now, and is fully managed, could we kind of MacGyver a DynamoDB table to perform like a relational database? What would that even look like, to stuff an entire relational database into a DynamoDB table? Well, I decided to find out. So I took a relational database, and I decided to put it into Dynamo. And the database that I chose will look familiar to you if you were anywhere near Microsoft Access in the 1990s, and that is the Northwind dataset. Anybody remember this? Yeah, for sure. Or like AdventureWorks for SQL Server. These were these sample databases that ship with these Microsoft products. A lot of us have some schadenfreude, I think, when we look at this. But this was supposed to be an ERD, a crow's foot diagram for some spice company. I don't know what the narrative was. But you see it has all the normal little tables you'd expect for a line of business app: orders, products, customers, a few other things, suppliers. You can get all this data on GitHub now. All the Northwind sample data is just like published as CSVs. So I went out and got it and decided to see if I could put it into DynamoDB. And I came up with a set of prescriptive steps that you can follow if you want to turn your own relational database into a DynamoDB table. And I will tell you up front, these steps are ridiculous. You should never follow them. They will not work for your use case, but they worked for Northwind. So take them, buyer beware, I guess. This is what worked for me. Step one, before you do anything, before you create a DynamoDB table, before you even have an AWS account, define the query patterns that you think you'll need. This is the exact opposite of the way you would design a relational database. How do you design a relational database? You spread out your data requirements, you figure out third normal form, you draw a crow's foot diagram, you make sure that you have theoretically consistent ways and referential integrity between all of your entities, and then you write queries against that, right? That's how you design a relational database. That is not what we're going to do. Instead, we're going to figure out up front what queries we need to run, and then we are going to design our DynamoDB table and shape our data very specifically to make those queries work. Will this data work for other queries? Probably not. But that's the whole point of NoSQL. Remember I said single purpose, not general purpose. So in the real world, you'd look at your existing system to figure out these query patterns, or you'd ask your users, you'd do some need finding. We don't have any users or an existing system, so we're going to make some up. So I looked at the ERD and I came up with some possible query patterns for the Northwind data. Some of these are, excuse me, some of these are range queries, like get the most recent 25 orders. Some are lookups by ID. Some are lookups by other attributes. Some are actually many-to-many relationships. I tried to encompass a number of different things. So once you've done that, now you're going to create a DynamoDB table, and you're going to put 3 generic attributes on it: partition key, sort key, and data. And what do I mean by generic attributes? Well, I will show you. I want to jump out of my slide presentation here for a second, and we're going to look at some code. And actually, before they do that, I'm going to grab a drink of water real quick, if you don't mind. Apologize. So, for those of you who are new to AWS, you are now going to see a DynamoDB table being created in real time. I know, it's very exciting. So I'm using the Python API for AWS, which is called Bado, to do this. And you can see I'm doing DynamoDB create table, and I'm creating a key schema. So I've got a primary key, a partition key, if you will, on my table, which I'm giving the attribute name PK. Right away, this may seem odd. Why am I giving it a name like PK and not the name of what it actually is, like, I don't know, order ID or customer ID? That's because there's going to be all kinds of different things in this attribute. It's not going to be just order IDs. It's going to be a bunch of other things as well. Same is true for my range key, which is sort key, SK. There's going to be a lot of things in there. And then I've got a third attribute called data. And I'm going to put a lot of things in there because I'm going to define what's called a global secondary index on my table. Don't worry too much about what global secondary indexes are, other than to know it's an index that provides essentially a complete separate view into your table. You can define these at table creation time or later on in the life of your table. You can project different attributes in them so they don't have to be as big as your entire table, but it's like a copy of your table that you can query using a different key. And DynamoDB in the background will replicate, so you don't have to worry about keeping these things in sync. So the partition key of our index is going to be the sort key of our main table, and then we're going to use this data attribute as the sort key of our secondary index. We're going to project all of our attributes in here, so everything that's on the main table is also going to be on our index. And then we're going to use pay per request for the billing mode. This is that new on-demand thing that we finally have. It means I don't have to provision and pay for any capacity that I'm not using, so that's exciting. I am going to go ahead and create this table in AWS, and I'm going to use this script to do that. So let me quickly get back into my AWS account. I'm using a command line program here called Awesome. This is a pretty cool open source tool that Trek 10 has released that makes it easy to manage a bunch of different AWS accounts. If you're curious about this, let me know. I'll make sure you have the link to it on GitHub. And I'm going to run my script. So I'm going to do setup. This will create my DynamoDB table, and it's going to load all the Northwind data into it. Notice it says it's waiting 60 seconds for the table to create, not because I'm checking the status of the table in Dynamo, but because I'm an elite hacker, and I put a time.sleep of 60 seconds in this script. So I'm super cool. This is what the AWS Management Console looks like, by the way. Let me go ahead and wait a second for this to finish, and then I'll show you what that table looks like. I do have all of the CSV data for Northwind in here, so this script is loading all of that in there. This is orders, shippers, suppliers. I don't have every single table, but I have the big ones. I left a couple of sort of ancillary ones out, so I didn't have to worry about them. 60 seconds goes by, and let's see if I can show you what's going on here. All right, so my session has expired. I'll just flip over here and jump back in. So I'm going to go to my US East 2 region, which is Ohio, where I created this table. And the table should be called Northwind. And there it is. So it's active now. Everything should be good. Does it have items in it yet? It does. Hooray. Yes, so it's okay. It finished loading my items. So I don't know how much all is in this table, but this is what a DynamoDB table looks like. Let me zoom out so you can see this a little better. Is that still reasonably easy to see? Pretty good? Yep. That's not too small, is it? Okay. So that probably looks like gibberish, and it should. We'll talk more about why it looks like gibberish, but you see my three generic attributes here: partition key, sort key, and data. And the reason that I am creating these generic attributes is so I can do something called index overloading. So let's go back to our slide presentation here for a minute. Index overloading is the concept that we have a limited amount of things we can do with a single index on our table. Traditionally, we would just do a key value lookup. Wouldn't it be nice if we could use those indexes for more things? So we're going to stuff not just product records into this index, but also order records, employee records, all kinds of things are going to happen. And that's very counterintuitive if you're used to a single field having multiple records in it, but that's what we're going to do here. So once we've created that DynamoDB table, we're going to create an item in the table for each record in every entity table that was in our ERD. So not join tables, things that are mapping many-to-many relationships. We're just going to focus on the entity records for the moment. And I call this playing Tetris with the data because, again, we're trying to stuff as many different access patterns into the smallest number of indexes that we can. So we've got two indexes here, the main table partition and our global secondary index. And let's look at what we're doing. We've got the partition key for the main table is pretty much just the primary key for every entity in our relational database: orders, products, employees, categories, shippers, suppliers, and customers. But the sort key, we've put all kinds of random stuff in here. For orders, it's a static value called order. It's the category name for categories. What governed what attributes I put in here? Well, simply put, it's the access patterns. I know that I want to be able to filter employees by who they report to, so I chose to put that in my sort key. This is completely bespoke based on the access patterns I defined as step one. And same is true for the sort key on this other index. What are all these weird things like these hash marks? Well, that's what we're going to talk about now. There are some tricks, many tricks in fact, that you can play to get the most out of your indexes. There's three that I want to show you in particular, and I'm going to show you those, I think, by going back to the table, because this is more fun to look at in action. So static GSI partition keys, hierarchical sort keys, and sparse indexes. What do I mean by this? All right. So I've got this table, and I've got the table partition, and I've got my index, GSI1. We'll switch to query mode here, and I'm going to show you this in real time. Let's look at all of our supplier records on the table. So I'm on my secondary index, and I'm going to sort by this, or I'm going to search by this static value called supplier. And what this is going to do is bring back all of my records that have the sort key or the partition key on my GSI of a static value of supplier. That's that static value that I was talking about, static GSI partition keys. And I'm doing this to get past the fact that I removed my unique names from these attributes. So I can no longer query on an attribute called supplier, so I'm putting supplier in the value of the attributes. You got to be really, really careful with this, because effectively now I've stuffed all my supplier records for that GSI into the same partition. So that means a hot partition, lots of accesses going potentially to one shard on my underlying NoSQL database. So I need to be careful and not have too many records in this partition. I might need to shard that out, create some randomization on there if this got a lot bigger. But because I can do that, I can actually do one of the queries that was in my access patterns, which is I want to look up suppliers based on their country and region. And that's the second trick. Look at data, which is, again, my sort key for the GSI. See how it's country, hashmark, region, which is null for non-US countries, and then I think that's city, and then there's address. So because I've squashed all of this into one index, this is called a hierarchical sort key. I can search for, I can actually filter my range here based on what this field begins with. So let's suppose I was looking up the suppliers that are in Massachusetts. I can do USA for the country, hash MA for Massachusetts, and start my search. And that's going to pull up the one supplier I have that's in Massachusetts. So right away, I mean, I'm looking up by country and by city, excuse me, by country and by state. I'm filtering on a particular type of record out of my giant NoSQL table, and I'm doing all of this with just a single index. It's pretty efficient use. The other thing that I wanted to show you was sparse indexes. And to do this, I'm going to go to the product record. So again, the product records also have this, there, we'll get rid of this for a second, this static sort key. So if I start my search here, there's all my product records. And notice how some of them have this data field at 0 or 1. It actually shouldn't have anything. I didn't clean up the Northwind data enough, but this just means whether the product's been discontinued or not, 0 or 1. If I wanted to, I could get rid of this data attribute, this 0 for products that aren't discontinued. Then the only data fields for product records that would be populated would be discontinued products. That's called a sparse index. It makes my product partition a whole lot smaller. And then I could do something like, sort key equals 1 or whatever, and search on that, and it would just bring up my discontinued products without having to search the entire product partition. Again, that's called a sparse index. It's just a little bit more performant way to access your data. All right. So bringing it back to, well, let's address a quick side question. Why are we so obsessed with packing a lot of stuff into a small number of GSIs? The answer to that question, there's a couple answers to it. Until very, very recently, like November of 2018, there was a hard limit in DynamoDB of 5 GSIs per DynamoDB table. They have finally released that limit, and it's now a soft limit of 20, meaning if you need more than 20 GSIs, contact AWS, they'll probably give you more. But you can, even if you can put as many on that table as you want, they're still not very cost effective, either from a performance standpoint or from a dollars and cents standpoint, because think about what's happening when you create a GSI. There's replication that's going on under the hood. Anytime you write data, it's got to not only go to your main table, it's got to replicate out to all those other indexes, and that costs you capacity units, it costs you money, and it costs you performance on your table. So you really, really want to try to pack your data down into the smallest number of indexes that you can. So going back to our list of things we want to do. Define the query patterns you think you'll need, create a DynamoDB table with attributes, generic attributes. You'll create items inside those generic attributes. And then finally, we've got these many-to-many relationships we want to represent. So going back to our ERD here really quickly, just a reminder of what this looks like. We've got some many-to-many relationships here. Let's see, do I have a pointer on this? That would be cool. Maybe I do. Oh, I do. No! Why? Okay, that seems to work. All right, so back we go. All right. So here's some many-to-many relationships. This big one here is called order details. And you can see a single order can have many products inside of it. A single product can belong to many orders over the lifetime. of the product, and then the attributes of that relationship are captured in this little join table here called order details. So we haven't represented this relationship in our DynamoDB table at all, and that is what we're going to do. There's a couple other many-to-manys. There's one there and another one up there, but they're kind of ancillary, and I just didn't care. So we're not going to put them in. So let me show you what this looks like. All right. The concept we use to deal with this is called adjacency list. This is a concept we borrowed out of graph theory. And if you think about the entities in our Northwind database as nodes from a graph perspective, you can think about the relationships between those nodes as edges. So we're going to create some edge records, some new items in our DynamoDB table to represent those many-to-many relationships. You got to be careful here because this kind of denormalizes your data a little bit further. It's not too bad here because Northwind was nice enough to give us some records already, but in a non-perfect world, we might have to take or create out of whole cloth new records for DynamoDB that contain some attributes of the order table and the product table. And anytime we write to orders or products, we've got to update that order details. But what this looks like is this. So we've still got our order records up here. This is the entity records we created before. I don't know why it keeps doing that. Sorry, guys. Just saw my rest of my presentation. These are the order records we created before. These are the product records we created before. And now we're creating some new order details records. So for each one, it's going to have the same partition key as our order, meaning that we can query the main table to look up not just the order, but the products that are inside that order. And then we're going to make the good grief. We'll make the sort key. I'm just not even going to try to do that anymore. We're going to make the sort key for the main table the product ID for those product details. Let's go back to our table, and I'll show you what I mean. So if I query on a particular order, I happen to know, I'm going to go back to my main table index here, so this is not the GSI. I happen to know that there is an order with the ID 10264. So I'm going to search on that. And here is my order record, so it's all the details for that order. You can see them there. And then I've got two more records that come up. They've got the same order ID, but they've got a sort key of the product that is inside that order. So here's the two products, product number 2, product number 11, that were included in order number 10264. Now that's one side of the many-to-many relationship. What if I want to do a reverse lookup, and I want to get, for example, all the orders that product 2 has belonged to? Well, for that, I just have to switch to my GSI, and then I do products #2. And look this up and look what I get. Boom, there we go. So it happens to be the case that the only sort key records that have a prefix of products hash are going to be order details records. There's no other item in my database that has, or in my table I should say, that has a sort key of products hash whatever. That's just something that you have to know when you're designing your data. So that's why this query works. But that gives me all of the products that all the orders product number 2 has been associated with, and you can see there's 44 of them according to this count up here. So there we go. We got both sides of our many-to-many relationship. That's what adjacency lists are. It's kind of a slippery concept if you try to read up about this online. I read probably 5 different things about adjacency lists. They all said different things or explained it in a different way. So, you know, this is what I say they are. And it sort of works. So let's pretend that's true. All right. So back to our next step. What have we done? Last thing we need to do, you will be sad to know, I'm sure, that every single database in the world cannot be represented in DynamoDB with one table partition and a single GSI. You will reach a point where you need more access patterns and you have to put more indexes on your data. So this last step, as needed, would just kind of be to circle back through steps 3 and 4 and either create more GSIs, split your data, denormalize it even further into smaller items so that you can run more queries using the same number of partitions, or potentially to do something else entirely. But in this case, we're going to be able to handle all the query patterns that I showed you up front using just those 2 indexes, and it would look like this. So don't worry too much about this. The main thing that I want you to take away from this slide is that all of these queries wind up being really simple. I don't have to do any filtering where I query an entire partition and then filter it on the database side before it's returned. That's not as efficient. It's not terrible, but it's not as efficient. Instead, I'm able to do all these lookups conditionally right on the indexes, which is blazing fast. This is how you want to use DynamoDB if you can get away with it. What are my trade-offs here? Well, actually, let me stop there first. Questions? Yes, sir.
The adjacency list solution here, I get what you're doing with the hash key, using the sort key kind of as a grouping, and you go both ways, and that works.
Yep.
You like it. But could you contrast for that, what if I had come up with a different solution where both of the primary order support.
Mhm.
What if those rows had arrays that pointed to all the other objects? So instead of having individual DynamoDB rows for the JSON relationships, they were actually buried in the JSON.
Right.
Very contrasted.
So you're describing more of a traditional document DB structure where you're representing everything inside of one giant document. There's definitely advantages to that. The problem you're going to get there is going to be speed of lookup across a whole lot of different things. So you would be talking about then, you've got multiple documents that all contain information about what they point to, correct? Well, I shouldn't say speed of lookup. That's really going to be more of a write time issue, right? Yeah.
The idea is, one of the pros I saw when I was thinking this, because when I was looking at your cool solution here, was Dynamo charges IOs. What I suggested would probably result in a lower amount of IO usage on the table in total
For sure.
For a given data set. But usually the world doesn't give us pros without cons. And I actually could come up with a con. So I was actually hoping you would tell me what you didn't like about it.
Yeah, so the con that I can think of is that when you do have to make that right, it's going to be tougher to keep that in sync, right? Because anytime you change one of those relationships, you got to go touch every document that represents one of those relationships. So actually, your read is better, but your write gets a whole lot worse.
Gotcha.
Does that make sense?
Yeah. Let me push it just one more step since nobody else had a question. Am I right in assuming that you're really taking advantage of the fact that Dynamo has a sort key? If it were a true O1 and didn't have this extra cool thing, that the adjacency would be harder to do?
Yes, correct.
Okay.
Yep,
So
absolutely.
Really you know Dynamo, you know how sort keys work, and you're really,
Yes.
I don't want to say abusing it, you're fully exploiting it to maximum potential.
I think exploiting is a great word. We're exploiting the heck out of that sort key. Yep, for sure.
Thank you.
Great question. Other questions?
Don't all NoSQL conceptually, you can always produce another table, which is the sorted, primary index of your table sorted in for access to the key for your other record and then pull it directly.
I can't speak for every NoSQL database out there, but a lot of the patterns that I've shown here actually do apply pretty generally to NoSQL databases in general. Yes, sir?
If I understand what you're doing there, you're sticking all this into one gigantic database. Right?
One gigantic table, actually, yeah.
What's the advantage of that over splitting it out into separate tables? That way you don't have to worry about any potential conflicts. Because the last query you showed there was you knew that when you certified product ID or whatever it was,
Yes.
no one else is going to, you specialize that query.
I specialized it, correct.
So what's the advantage of one gigantic one versus, in essence, one table per view?
Very good question. Everybody understand what he's asking? So there's a couple of advantages. One is around data locality. One of the big things with NoSQL is we are trying to move our data closer together to support fast accesses at large scale. If you split up your data into multiple DynamoDB tables, these things are going to be living on different physical machines. They're far away from each other. If you ever need to run a query that is, for example, looking up products and orders, like I showed you before, those are, you'll have to make multiple queries, so you got HTTP latency introduced there, to multiple data sources. You got to bring that all down, then you got to write application logic to query it. Now, in our use case, that might not be that big of a deal because there's not that much data in here, but you multiply that out to a larger scale, and you multiply that across many, many potential tables that you would need to be working with, and you start to run into more problems.
So, but I want to make sure I understand what you're saying though, because if you, for the example you just gave, you have to do two separate queries to two different tables. Don't you still do two separate queries to this one table?
No, this was one query to one table. For either side of the relationship. So it was one query to look up orders based on product. It was a different query to look up products based on order.
Right, that's what I'm talking about. If you had to do two queries here, you can still split it out to make sure it's two queries to two separate tables.
You could, but think about what would happen once you wanted to run a different query that was not one of the ones I just mentioned. Instead of, well...
But you couldn't because you have to specialize.
Okay, hang on a second though. So talk about what you're describing there. Why would what you're describing not require two lookups to get products based on order?
No, I think you do. I think my point is I think you have to do two lookups whether it's one table or two tables.
So let's...
You have some specialized queries for here. You can't just randomly pick a query you want to do unless you just happen to get lucky.
Correct. You're exactly right. We're going to talk about that in a minute. This does not generalize well at all.
Right.
You're
So
exactly
in
right about
essence,
that.
Every time you want to create another view of your data,
Mhm.
you in essence are adding more rows to this one table for those specialized views.
Mhm.
And I'm saying if you want to do two queries, one over the new view you
It is, but now you've got to keep 2 different tables in sync as well.
Yes, but
You know?
and I understand that.
And you're also paying double the cost.
Well, that's what I was wondering. What is the cost difference there? Because you should technically have the same number of rows in one table versus 2 tables. Is there a cost difference from?
Now, can you help me understand why you have the same number of rows? Because it seems like if you're trying to materialize a different table for each view, there's going to be an awful lot of duplicated data because some of these views are going to use same pieces of data.
I guess let me go back to whether I actually understand everything you're doing here. Because I'm interpreting what you're doing here as every query is like a different view, and every view has its own set of rows in this one table. Because it's so specialized, you can't use that view for anything else but that one query of that view. So if I wanted to have a different view that's ever so slightly different than the previous one, I got to create a whole other set of rows just for that view. Even if the data looks awfully similar to the previous one. It's not exactly what I want, so I got to duplicate the data.
I don't think the mental model underlying those questions is quite right.
Okay,
I
was wrong.
It's all good. So there is no duplicated data really in this table right now, unless you count the order details records as duplicated, but they were already present in the Northwind data set. I didn't create any new records that weren't already in Northwind. When you run all these different queries, I showed probably 4, 5, 6 different queries there. Those are queries over my segments of the various partitions on my table. But there's no duplication other than what's required to replicate the data into that index. So from the perspective of every time I create an index, there's duplication that I'm paying for in terms of write capacity being consumed. That is true. But there's not duplication in the sense that I have to write records myself and maintain them and keep them in sync. Does that help to understand? These are really good questions.
It does help, yes.
Yeah, okay. Yes, sir.
I'd like to pin the conversation and just maybe comment on it further.
Sure.
That people in the room might not know. Dynamo, you provision per table. So if you're not doing the 3rd category you described, pre-provision or even the auto scale, you have to micromanage the I/O per table. And I've found that that's difficult. I prefer to have one table and say my whole company requires 1,000 IOs. I found that to be meaningful. I don't know if you want.
I think that could be meaningful for sure. Yeah, you've got to think a lot about what the cost is of your solutions, both from a performance perspective and from a dollars and cents perspective. And putting stuff in one table tends to make both of those conversations easier to have. But I'm not defending this as a panacea of database design, to be clear. We're about to talk about a bunch of trade-offs of this. Really, really good questions. I love it. Anybody else have anything? We're not really in a rush here, so.
Well, your access patterns are all read-only.
They are, yes. We did not talk about write patterns at all. So write sharding on DynamoDB is really interesting. It's probably another whole talk because, should we talk a little bit about the underlying architecture of DynamoDB, or is that too much for this?
I would vote yes.
Okay, I don't have a slide for it, so there's not pretty visuals.
It might help. It might give some context.
Okay.
More data, not less.
All right, and shoot me if I'm saying something wrong, because not all of this is super fresh in my mind.
Wrong state for that, man.
Thank you. Hey, I'm from Virginia. Don't worry about me. But you've got the way DynamoDB is implemented under the hood. Obviously, it's horizontally scaled. You've got individual pieces of compute. I think it's something like 10 gigabytes is the maximum on a partition, which is a chunk of compute, and then it scales out wide. So what that really means is that for an individual partition on a table, which is a single hash key, that's got you can only get up to so much capacity on that partition before you start to get throttled. That was true of DynamoDB until the last year or so when they released something called adaptive capacity, where if they saw you were hitting a single partition key over and over again and starting to throttle, they would dynamically allocate more partitions to that hot key, which is super, super cool. And they didn't even really advertise it when they did it. People just started noticing their queries got a lot better, and then finally they publicized some information. Where was I going with that? So that's kind of how DynamoDB is built. What was the question you were asking?
I mean, you were going to go into like the write.
Yes. So sorry, I'm getting a little bit spaced out here. So the write piece, how do you access more? How do you get more for your money from a write perspective? And I think the best way to do that is to provision your table such that still, you're okay. There's a formula that's involved here, and I think I better find it and put it on the screen because I'm not going to try to quote it from memory. That would be horrifying if I were to do that. You guys cool if I put a scary formula on the screen? Okay. This talk is going off the rails. Look and see, all these links are purple. Okay, so if you're concerned about hotkeys and you're concerned about too many writes going to one of those single 10 gigabyte partitions, how do you distribute the space? Well, you expand the space. You can add a random number to the partition key values to distribute the items. I mentioned this briefly in passing a few minutes ago. Or you can use a number that is calculated based on something you're querying on. All right, let's see if we can find the, oh crap, the cool formula is not on here. But essentially you come up with a number of partitions you think you're going to need, which is a number n, and you do some math on it, and that gives you the random number that you need to append to your partition values in order to make sure that you've randomly spread them across your write space. That's something that we would need to sit down with a pencil and paper for a very specific use case. I'm not going to provide prescriptive guidance about that up here, but that's a whole interesting conversation. So yeah, that's why we didn't get into writes in this discussion. Yep. Great question. Okay, shall we go back to our presentation for a moment? All right. So trade-offs, besides all of the things we just mentioned. If you get this right, it will be fast and scalable. DynamoDB delivers as advertised if you take full advantage, if you fully exploit those partition and sort keys. But a single table model, I like to say, is both informal and it's also inflexible. It's informal because there's no referential integrity. There's no magic wand in the database, or there's no whip that's cracked over you to make you store your data in any particular format. Remember that when I said that I knew that only a certain set of records was going to have a sort key of products hash this? I only knew that because that's how I stored the data in there. There's nothing preventing me from messing up one of those records. So it's informal, but it's also very inflexible. This is the point you were making. If I need a new access pattern, I'm probably going to have to rebuild my table. I'm going to have to play a whole new game of Tetris to refit everything into those few indexes, or I might need to make new GSIs, which again has a write cost. Or I might need to break my items out even further, which becomes a management issue. What I really, really wish existed here, there is no tool to my knowledge in the world that does this, but I wish there was something that would take those access requirements, like what we discussed at the beginning of this section, converted them programmatically for me into an optimized DynamoDB table, and then provided me an ORM, so I didn't even have to know what indexes were being used or what the attributes were named. That would be freaking awesome. Okay, so if you want to write that, let me know. I've spent a little time thinking about it, and I'm not sure I could come up with something general enough to be useful. But that is a really interesting project if somebody wants to win fame and fortune. Because, as my last point here says, those optimized single table layouts are not very human readable. One more time. Yeah, let's put this back in front of us just so that we can remind ourselves how bad this is. And I mean, this isn't even really that bad because, let's go to the whole table. Just being honest, I mean, like I have my sort keys named things like product is in the name, and a lot of the primary keys have the name of the record in them. But if you look at a real single table DynamoDB design where there's randomized values in here for write sharding, and there's unreadable, GUIDs in there, and all the attributes are generic, there's no way to know what's happening. I mean, it looks like machine code. It doesn't look like something a human spit out. The problem is it takes a ton of human intelligence to make that machine code looking thing. And that's a huge barrier for a lot of people and not something I'm trying to discount at all. So that brings us back, of course, to the question we sort of asked at the beginning. Why should I do any of this when relational databases are still right over there? And I'm not really saying that you should. The reasons, too, I think, are if you're doing serverless on AWS, you want the advantages that DynamoDB brings to a serverless architecture. Some of the things we discussed, again, scale, HTTP API, we can go over all those, fully managed. And you think your access patterns are stable enough or you're confident enough in DynamoDB to implement this, you can feel very, very happy and proud of yourself. And your application will be happy. But there's a lot of trade-offs to consider. Remember that article I mentioned that I wrote a year ago about DynamoDB and how it's not for everyone? I ended that article with this flowchart for when you should use DynamoDB or when you should not. I fully expect you can't read that from where you're sitting. It's probably kind of blurry. But I'm just putting that up there to show all the trade-offs that there are. At least one of those bullets isn't valid anymore because they have backup and restore now, but most of this is still the case. And what it's saying is DynamoDB has actually a really low barrier to entry. It's easy to start throwing JSON in there. It's fully managed. It's sitting there for you in the AWS console. So it's great for toy projects, great for hobby projects, especially now that they have that on-demand access and you don't have to pay for the capacity. when you're not using it. But if you're going to back a serious production workload with this, you better be sure you know what you're doing, and you better be sure you have a development team that's willing to put in the time to learn it and to relearn it and rebuild it, as some of the warnings in the DynamoDB documentation take on an unpleasant tinge of reality. So yes, those are my DynamoDB caveats. Any more questions about that before we move to our conclusion, our epic conclusion? All right, so takeaways here. There is no silver bullet. You all know this when you're designing things. This has not been a talk about how to pick the right data store for your application. There are many, many NoSQL data stores out there that work well for serverless. There's a guy named Rick Houlihan who works at AWS. He's a NoSQL expert, and he did a talk at reInvent this past year about how to choose that right workload for your app, which I will not rehash here. But he has a concept called the PIE theorem, P-I-E, which he's playing off the CAP theorem. You guys know CAP? It's the idea that you can't have both consistency, which is C, and availability A in the face of a network partition P, CAP. And that's underlain a lot of database design decisions over the years. He proposes PIE, which I think stands for pattern, let's see if I get this right, pattern flexibility, infinite scale, and efficiency of queries. And the idea is you can only have 2 of those 3. And he puts a lot of different things like relational databases, graph databases, document databases on that spectrum. Data warehouses fall in there. That's something for you to look up on your own. But there's no silver bullets. That leads into event sourcing, polyglot persistence. Optimize for flexibility early. This is where event sourcing really, really helps you, because you've got that single data source that is sort of turned inside out and decomposed into a set of events, and you can plug different views into that depending on what you discover that you need over time. It's actually very freeing to realize you haven't locked yourself into a single database choice that's not going to pay dividends down the road. But of course, you do want to converge on the best fit. So you want to be paying attention to your application access patterns, writing down those query patterns, getting a sense for how closely you can match what you're doing onto the capabilities of your data stores. And then don't drive with the emergency brake on. Obviously, DynamoDB is very, very easy to drive with your brakes screaming in protest if you choose to ignore some of the best practices that they put out there, but even if you just try to run it like a database that it's not. And that's true for other types of databases as well. I want to provide you with some resources here. If I had to recommend you to read one thing coming out of this talk, it would be a book by a guy named Martin Kleppman called Designing Data-Intensive Applications. Anyone know this, have it on their shelf? Somebody does? Great. Did you really? Excellent. If you made a New Year's resolution this year to read more and you have not read this, I would highly recommend putting it near the top of your list. He goes into the event sourcing question a whole lot more. He's got a lot more really practical takeaways on how to build systems that are distributed, that have Byzantine failures. It's surprisingly readable for all of that. 100% recommended wholeheartedly. Say it again?
How old is it? When was it written?
This, I think, came out in 2017.
Okay.
So it's very up to date, yeah. Yep. Very, very good. And then Rick Houlihan's name I already mentioned. There's another talk he did called Advanced Design Patterns for DynamoDB. This has been floating around social media for a while, partly due to me plugging it wherever I possibly can. He gets into the DynamoDB modeling a lot more. He gets way farther into some of that right sharding and other things. Watch this, be amazed, but beware. Rick is a NoSQL wizard, and he will show you things that look easy when he does them, but probably should never be attempted by mere mortals. Okay? So don't watch that and then go away and do what he's suggesting unless you're really sure you're prepared to walk down that path, would be my advice. But definitely watch it, even just for entertainment value. Okay, and then the last thing would be everything in the second part of this talk is also contained in a blog post, which you see the link for right there. All of the code for how to build the Northwind table, and I've actually got all the queries that you need to run against it defined. That is all on GitHub. It's available. And there's even some suggestions in the blog post for how you can change the table to support a given access pattern. I was thinking we might try to take a few minutes and do this as a class exercise. I'm not sure that we have A, the time, and B, the interest in AWS as a group to do that, but I will leave that up to you. Do you want to play with this more, or do you want to be done and maybe take this as homework? I'm fine either way.
So I have a question that I haven't asked yet that I've been holding to the end because it's not really a serverless question, and it's certainly not a DynamoDB question, but it is a NoSQL question.
Okay.
So here's the scenario. I wanted to do a graph network of followers and friends from Twitter.
Mm-hmm.
So got Twitter API, and I'm implementing in Python, and I got a Bitnami MongoDB stack and implemented it in a VM on the same box.
Mm-hmm.
Everything is great. Getting the timings down with going to the API and making that timing to the API that's metered match up with the accesses to the database so that everything seems to work together and you know, optimize both, hitting both servers,
Mm-hmm.
if you will. But one of the issues was that Python has a constant time access to test existence. And I didn't find the same in MongoDB, and I couldn't get MongoDB efficiently to give me the index table. What I had done with MongoDB's table is I'd used the indexes from Twitter as the primary key instead of letting it invent UUIDs. So I got efficient access for any Twitter ID. But if I wanted to say, does this exist, I'd have to go and test the database by reading the record. I couldn't say, take all of these IDs and tell me whether, how many of them don't exist or how many of them do exist in the database. And I also couldn't ask it to give me efficiently from the NoSQL database the index table, which is what I wanted. You know, I wanted basically what's already in there. I want to just store that back like a Redis table in my Python. Does DynamoDB suffer from the same limitation as Mongo? Is that a problem for people that are using the primary index? You know, you were using secondary indexes and you've got a much more complicated relational thing where you're letting the back end do more of the work.
Mm-hmm.
In my case, I just want to build out this relationship in, you know, in memory. And there were some issues with Mongo only allows for a certain size, record size. After that, you would blow it. So even if you're just storing ints in there as like friends, an array of friends or whatever, you would blow one record, so you'd need to have backup records behind it. So there were other problems like that, but basically the issue of extracting the primary key and what have you from a NoSQL database didn't seemed to be something that everybody would want, but there was no reference to it in the MongoDB literature.
Yeah, I mean, you're effectively scanning the partition if you do that in DynamoDB, which is potentially going to be slow. You could,
yeah, it was slow.
Yeah, you could create an index on that and you know, not project any other attributes into it, in which case it would be faster. Or if you wanted to, you know, there were only certain records that contained a value you were interested in, you could just project those into an index, and that would help you even more because you wouldn't have to touch other records.
I could have taken my tables and at the end stored them out, updated them into a record of themselves, so that I could say, okay, here are all the indexes that I know about that I want to look up.
Yep. Yeah, I mean, there's ways to do it, but you know, that's what makes this fun. You got to look at the. I can't speak too much to MongoDB. I'm not an expert on that database technology at all. So I can't help you too much there. Yes, sir.
You actually said earlier we could defer this question until afterwards, but maybe you'll answer it in front of the group. Do you use the CloudWatch event bus as opposed to
Yes.
Kinesis?
Yes.
I'm really curious about that.
Of course.
You wanna tell the group?
Yeah, I think that's a great question. So if you recall, we had a CloudWatch event bus that we were using as our ledger, as our event source, and traditionally, a ledger-based architecture would be built around something like Kafka or Kinesis. It's streaming, it can process a ton of records. There were a few reasons we didn't go with that. Number one, we didn't need it. There were not enough events coming through this system to make the cost trade-off obvious. You reach a point where CloudWatch events gets way more expensive than Kinesis, but because you're paying for Kinesis by the shard hour, there's a base cost that's higher. So there's an inflection point there, and we were not high enough above that inflection point where it was an obvious choice to choose Kinesis. And much more importantly, Kinesis, as you know, if you've tried to build a Lambda-based architecture around it, has a limitation on the number of consumers it can have. You can have a maximum of 5 consumers off a Kinesis stream. So fan out becomes challenging because you've got to fan one Kinesis stream out into a bunch of Kinesis streams. And if you have a very spread out organizational structure like we had in the company we were working with, where you had many different teams all over the world who were all trying to develop their own consumers and producers against this ledger, it became a lot harder to vend out access to the bus to them using Kinesis because you had to, again, maintain all these fan-out systems and everything than if you use the CloudWatch Event Bus, because CloudWatch Event Bus is specifically designed to make it really easy to couple different AWS accounts together. Forwarding events between AWS accounts via that bus is as simple as just exchanging AWS account IDs. You don't even have to go through the process explicitly of setting up a full IAM trust relationship. That happens for you under the hood, but it's mostly abstracted away by AWS. It's very nice. So those were a couple of the reasons. There were other things as well, but that was the primary driver. Great question. Yes, sir.
So you mentioned the iterative process of kind of exploring serverless and NoSQL. What type of metrics do you look for? Do you just pull some of the telemetry data out, or are you looking at graphs that show the pricing and say like, whoa, we're starting to get into these thresholds? Could you talk about that?
Talking about as you converge on that best fit, kind of? Yeah, I think that would be definitely a large part of it. You'll start to get a sense, and the developers in the room know this, where you start to feel, as if you will, the brakes grinding on the app when you start to have it asking for queries that it doesn't want to give you. And so I think the big metrics would be query latency, and then of course the cost as you start to scale out. Something like Elasticsearch, AWS has hosted Elasticsearch, which made sense for the architecture I was talking about because we knew our data was not going to grow at a huge exponential rate. It would be a slow creep, which is easier to manage when you have to deal with capacity yourself. So if all of a sudden that data started growing hugely and we were changing the cluster size like twice a day, that would be the time to move it onto a data store that scaled a little more automatically, right? So yeah, you're right on track. I saw a couple other hands start to go up. Yes, sir.
So in the inventory management
Yes.
application again, you use Snowflake DB
Mm-hmm.
as more or less, query, OLAP type.
Yes, data warehouse use
Why
case.
not
Yep.
use Redis? What was the
You must mean Redshift.
yeah,
Yes.
sure.
Yep. Yeah, Redshift and Athena are a couple of competitors in the AWS space to that. And it's a good question because we are an AWS shop, so we tend to use AWS tools when they make sense. But it made a little more sense to use Athena than Redshift because we were looking at doing semi-structured data. And when we ran the benchmarking, I think Snowflake had 10 times the performance that Athena did for the structures we were working with. Athena is great if you have columnar formats for your data and you organize it specifically that way. But we had far, far better performance in our benchmarking with Snowflake. And also we really like the price model compared to Redshift, where it scales up from 0. Those compute capacity units, they call them, go up specifically as you add data and as you query it. The warehouse, which is the compute, is decoupled from the storage. And you could have a ton of storage, but if you're not querying it, you're not paying at all for that compute capacity, which is really nice for us. I don't believe Redshift has that concept.
Okay.
Yep.
Sounds good.
I have a question.
Yes, sir.
I've been trying to make a migration from a Mongo system to serverless with DynamoDB GraphQL based API.
Okay.
But one of the biggest challenges that I have right now is that the pricing model of DynamoDB is super complex to understand. I mean, you have this like read unit capacities,
Yes.
and then write unit capacities, and then this is like split into 1 kilobytes and 4 kilobytes. And if you have like reserve, you
Right.
save like 6 times the price of on demand. So what are the metrics you're using, or is there any pattern where an app can migrate automatically from one system to the other?
In terms of migrating automatically, unless AWS's DMS supports that for DynamoDB, which I'm not sure I've seen. Actually, it may. I'd have to look into that.
But sorry if I interrupt, but I understand that if you use reserved unit capacities,
Yeah.
you can scale up many times during the day, but you can only scale down like 5 or 4 or something like that. Maybe I'm wrong.
I have to double check on that. You definitely get a savings with the reserve capacity for Dynamo versus on demand. I don't know quite what to say about the complexity of the pricing model, other than you just have to sit down and with a pencil and paper and work out the math. I'm not quite sure where to go with that question. I'm sorry. I don't have a lot of great advice.
It's complex to
Yeah, it's kind of expensive, and you got to sit down and figure out how much data you have and how much you're going to be accessing it.
especially because when you depend on authorization based on a budget, it's difficult to
Yeah,
keep a number.
yeah. Yep, I understand.
It's going to be more expensive to figure out the calculation than just pay for it.
That is really true, yeah. Yep. Yes, sir.
So it seems like the whole talk that you gave was, the assumption was that you have a company with a large amount of data and some history of query or access patterns. Does this type of setup still work for a startup that doesn't really know what's in the future as far as data? They don't really have a history of patterns, and they might be pivoting every month to something radically different.
Yes, if anything, I'd say it works better for a situation like that. The first part of the talk, I tried to cover that a little bit more. The event source pattern can help you again because when you're moving flexibly and quickly early on and you don't necessarily have all those requirements defined, it's really helpful to have the ability to plug different data stores in and out. In terms of how to define your query patterns for DynamoDB, I would not recommend, if you have really amorphous requirements for how you're going to access your data, I don't think I would recommend starting with DynamoDB. Unless, you know, it's such a small set of use cases or such a small set of patterns that it doesn't really matter. If you have, you know, a service that you're building where, yeah, you're just doing, you know, lookups based on an ID, and that's pretty clearly that's what that data is used for, then sure, put it in DynamoDB. But if you have unbounded relational requirements on your data, might be more interesting to look into something like, if you're on AWS Aurora, particularly the new serverless Aurora, although there are some challenges around that with scaling and security. But yeah, I think that you know, serverless lends itself well to building flexibly, and some of these data stores do lend themselves well toward that. DynamoDB does not lend itself well toward flexible access. Actually, let me draw that. Is there? There's not like a whiteboard in here anywhere, is there?
I get to the thing in the hall.
If I could draw that pi theorem thing for a second, I think that would really answer your question pretty well. I might even have an image of it saved I can put on the slide presentation real quick.
This will work. We can try it.
I think I've got a different solution. One of my many screenshots. Let's see. Look, I actually have it today. I screenshotted this to show to somebody today. All right, you see that? So this is not original to me. Again, this is Rick Houlihan. But the use case you're talking about is PE, pattern flexibility and efficiency, I believe. The thing that's not as important to you as a startup is infinite scale, because you're not very big. So that's where you choose something like Aurora Serverless, which I just said, RDS, which, you know, you're paying more for provision capacity, but there it is, Elasticsearch, or Neptune if you want to go the graph route. So that, you're getting access patterns, random access patterns, ad hoc queries. That's the flexibility piece. It's hard for me to remember these because really it should be FSE for flexibility, scale, and efficiency. The pattern and the infinite are added on to make the acronym work, but it's hard to remember them. Yeah, the infinite scale is not as important. Redshift and Athena, the data warehouse use case that I was talking about, P&I, that's where Snowflake DB falls. And then DynamoDB, of course, is infinite scale and efficiency. I mean, nothing's truly infinite scale, but, you know, for all intents and purposes.
I'm sorry, where does Snowflake fall?
That would be PI, yeah, with Redshift and Athena. And of course, these are only AWS databases on this because this was at reInvent. But does that help you a little bit? Yeah, great. Very good question. Other questions? This is good. We've still got a bit of time. Yes, sir.
Where's DocumentDB fall in that thing?
You know, DocumentDB had not yet been announced when this graph was made, obviously, because that was November, and DocumentDB came out like a month ago. But DocumentDB would certainly, I think, fall on the IE side, right?
Yeah.
Scale and efficiency, but it's not going to have that pattern flexibility. Most of the document databases would fall there. Now, again, this is a spectrum, so it might slide a little bit. You could think of it, I don't think that Rick would necessarily say this, but rather than just having your databases slide along those lines, you might potentially plot them inside the triangle a little bit. And so you might plot DocumentDB perhaps, or some of the MongoDB stuff a little bit more, a little farther up on the pattern flexibility side of the graph, but it's still going to be much more down toward the IE side. Any other databases you can think of that we should try to plot on here?
Well,
Oracle.
Oracle, that's way off the scale somewhere.
That's a Cape database.
That's right. That's right.
So there are many special purpose fastest scalable key value store. And according to the DB engines, the winner is Redis, but that's RAM-based, right?
Yeah.
So you have
Right.
to say, what is scalable? But there's people like the K people that do KDB, which is like an APL engine with special purpose hardware, and they make a scalable, on-prem server technology for implementing basically a RAM-based, fast as hell key value, or any relational database kind of concept. So the number of specialty databases is infinite, at least as far as I'm concerned.
Yeah, at least conceptually it's infinite.
Yeah.
Yeah, there's, right, it all comes down to the cloud scale. There's no Redis implementation, to my knowledge, that scales as wide as DynamoDB does
Well,
in the cloud.
one of the things you didn't cover here, and I saw that you went to Cleveland or Ohio or someplace for your database, is geolocating it, and how do you deal with geographic regions in terms of access to your database?
Anybody know why I chose to put that database in US East 2 instead of US East 1, which is geographically closer to where we are?
Probably because it affects latency and access, right?
It actually is not a latency choice at all. Yes, sir.
I'm probably going to get it wrong, but I've noticed, I'm self-employed and I do a lot of Amazon Web Services solution for customers.
Okay.
And I noticed that when I'm creating new accounts for them now, it's defaulting to that.
Yeah.
But I don't know why. But it's almost like the
Don't they do some balancing, or like with the prices?
prices different.
Yeah.
Yeah,
But
it's.
I think they price them differently to balance.
They do. Actually, I believe US East 2 to US East 1 is priced at inter-AZ prices, not inter-region prices, which is a cool fact that almost nobody seems to know. But yeah, so US East 2 is a newer region. US East 1 is the oldest region, and it also has the most customers in it. So if there's a problem, it's always in US East 1. Remember, like 2017, I think S3 had a couple major outages? Yeah, everybody remembers that. Half the internet was down. That was all US East 1 localized.
So, I mean, the reason I asked about geolocating is some of the, I don't like to slam cloud because obviously for a small business, it's one of the services you're going to buy. But there's a whole bunch of gotchas, and one of the pricing gotchas is picking up your data and putting it in a different geolocation. Because they charge for egress and ingress.
Oh,
and all
yeah,
that.
data transfer out is probably going to be your biggest, that and storage is going to be your biggest cost in AWS over time. It's not compute, certainly not with serverless. Compute becomes a rounding error, and the data transfer and the storage immediately becomes the big pain point on your bill. Yep.
You should consider a service that maybe has built-in geo-replication.
There isn't any, as far as I know, there's none of the cloud providers that has made that costless.
No,
It can be transparent to you,
sure.
but that doesn't mean it's costless.
Well, because it doesn't cost them nothing too. It's generally never going to be costless because it's costing them money.
Well,
there are services like Azure's Cosmos DB, where you won't pay for the egress of that data, but you're still going to pay for duplicate storage because at the end of the day.
So my theory is the more transparent it is to you, and the more seamless it is to you, the more it costs. I'm not sure of that, but I've done some looking.
Yes, sir.
Sounds right.
I have a completely different question. And you mentioned it in passing very quickly near the beginning of the presentation. When you were talking about the CloudWatch bus thing, and you said that you ended up putting, if I remember right, you ended up putting timestamps next to every column. And that, I'm just going to say that sounded weird to me. Could you expound a little bit on that?
Yeah, so do you know how Elasticsearch documents work? So you can think of just a giant grab bag of attributes that are indexed. And so we added, essentially we doubled the size of every document by adding a timestamp attribute that corresponded with every main attribute.
So I get that it felt, I don't want to be too critical because I don't have a better solution. It felt like an anti-pattern.
Okay.
But I don't have a better idea, and I'm very careful before I ever criticize
No,
something.
yeah, that's fair.
It felt weird that you needed to timestamp everything. Like, isn't there a solution in AWS that could have paired your data and timestamped it and lined it up so you didn't have to double your document size?
Well, AWS hosts Elasticsearch, but they're not providing much beyond that. So if you're going to put data in Elasticsearch, you're stuck using the tools that they provide. And Elasticsearch does have that concurrency control with versioning, but that's at the document level. It's not at the attribute level. So if you're going to make multiple updates to a document that may not be in the right order, you want to use the versioning to lock the document, but you want to check those attributes as well.
If you're not overriding or using the primary key like I was in my example, and you're letting the NoSQL database create it, isn't it likely that that UUID could be disassembled into your timestamp and a lot of other useful stuff that you could just take apart?
I have no idea.
Okay, so that's an internal thing. I mean, like only an assembler level guy would think about doing stuff like that, but I do, I take advantage of, somebody stored the primary key of the record has a hash of the geolocation it arrived from plus the timestamp of the thing, and if you take this field out of it, you can find the timestamp.
I remember at one point in my career looking at an API somebody had built that was, it had failed a pen test because it used, the resources were monotonically increasing, and you could guess other resources that didn't belong to you. Sure. And yeah, I mean, there's all kinds of things you can do with keys if you're not careful to randomize them. And what else? You don't have to have anything else. This has all been great. All right. Well, I will leave this up here in case you want to check this out, or contact me if you need this and don't have it. Like I said, all this code is available to you. To my knowledge, this is the only easily accessible playground for single-tenant DynamoDB design, or single-table DynamoDB design. So please check it out, extend it, play with it, have fun, tell me how it's messed up. It's just a starting point for people to have fun with. And I would like to thank you very much. So Patrick, can I give my 30-second pitch real quick? Yeah. Real quickly, let me say two things. Number one, I do work for a company. It's called Trek 10. We help people build serverless solutions. So if you need help with serverless, your developers are struggling and don't get the value add, let me know. That is literally what I do for a living. My non-professional or non-job pitch to you is I am a member of the serverless community, and I want to help you. So if you have a serverless question, if there's something that I can help you with, if you just want to spitball ideas or bounce an architecture off somebody, get technical review on a blog post, want ideas for a blog post, career advice, I would love to hear from you. So please feel free to reach out. My Twitter is there, my email is there. I do mean that, and I will get back to you. All right? Okay, wonderful. Thank you very much. You don't have to clap again. You already did that. You don't have to clap for me twice. You didn't have to clap for me once.